Hello everyone, this is Rashmita. I'm from IIT Bombay and I'm pursuing a BTech in computer science here. Today we'll continue with where we stopped at last session. Let me share the screen. So just 2 minutes, I need some adjustment for the editing of the part. Let's start with this session. I'm going on with the 23rd question. At 1127 Kelvin and 1 atmosphere pressure, a gaseous mixture of CO and CO2 in equilibrium with solid carbon has 90.55% CO by mass, and the equilibrium reaction is given as below. Calculate Kc for this reaction at the above temperature. For this, initially this is a gaseous reaction and the total pressure was given. So we can calculate the partial pressures by knowing the mole fractions. Here, the mole fractions were calculated using the mass percentage given. From the mass percentage, we got here that 90.55 percentage. So 90.55 grams of CO is present per 100 grams of the total mixture of CO and CO2. From that, we can calculate the mole fraction. The weight is 90.55 by 28, molecular weight by 90.55 by 28. This is number of moles of CO and this is number of moles of CO2. Here we'll get mole fraction of CO2 by writing moles of CO2 by total number of moles of CO and CO2. From this, we can calculate the partial pressures. As here we calculated the mole fractions of CO and CO2. From these two, we can obtain the partial pressures of CO and CO2 and CO2. As we know that we can write Kp as partial pressure of CO whole square by partial pressure of CO2. From this, initially we derived this relation, Kp and Kc relation for a given reaction in the last session. That is, I'll just remind you again, Kp equals to Kc into RT power delta Ng. Kc into RT power delta Ng. From that relation we can obtain the Kc value very easily. From this, delta Ng is 2 minus 1. That is the change in number of moles of gaseous products and reactants. We'll get that is 1, 2 minus 1. So Kc equals to Kp by RT. By substituting these values, we'll get a value of, let me calculate it. Calculations are a bit lengthy, but okay. Here we use some relations for finding the partial pressures of CO and CO2. From that, we obtain the Kp. From the relation between Kp and Kc, we'll get to know about Kc. From above calculation, we'll get a value for the Kc as 0.14. Approximately, this is Kc is 0.14. Sorry, 0.154. And next, we'll go to the next question. Calculate delta G naught and the equilibrium constant for the formation of NO2 from NO and O2. And they gave the reaction. For finding delta G naught for a reaction, we'll subtract the delta G naught of products minus delta G naught of reactants. We'll get this value. We know the relation between delta G naught and reaction quotient as delta G equals to delta G naught plus RT ln Q. This formula comes from thermodynamics. As equilibrium is present, delta G would be 0 and reaction quotient becomes the equilibrium constant. By substituting those, we'll get that minus delta G naught equals to minus RT ln K. By substituting the values, we'll get to know the value of K. But from this calculations, we'll get the value of K as equilibrium constant value as 1.36 into 10 power 6. Very easy. We use two formulas for finding the delta G naught value as well as equilibrium constant value. We'll go with the next question. Does the number of moles of reaction products increases, decreases, or remain same when each of the following equilibria is subjected to a decrease in pressure by increasing the volume? If we increase by increasing the pressure, volume decreases, so number of moles per unit volume increases. So we need to decrease this ratio, so number of moles should decrease. In this first reaction, number of moles will increase if the reaction proceeds in the forward reaction. But we need a decrease of number of moles, so the reaction would proceed in the backward direction to neutralize this change for the reaction. That is Le Chatelier's principle. Will generally Le Chatelier's principle says that if any change occurs in the reaction conditions, there should be a change in reaction to oppose that change provided in the surrounding. So to oppose this change, the number of moles should decrease. So the reaction would proceed in the backward direction. So the number of moles of reaction products in the first reaction will decrease as the reaction proceeds towards reactant side. And in second part, delta Ng for this reaction is negative. That is, if we go forward, number of moles will decrease. As per our condition, the number of moles should decrease, so the reaction should proceed in the forward direction. The number of moles of reaction products will increase in this reaction as the reaction is proceeding in the forward direction. For the C part, delta Ng is 0. So there will be no effect of pressure for this reaction. So the reaction remains as it is. It neither goes to the forward direction nor goes to the backward direction. So there is no effect of pressure on this reaction. Here, the number of moles of reaction product remains the same. We'll go with the next question. Which of the following reactions will get affected by increasing the pressure? Same as above question. Here, pressure is increased, so volume will decrease, and number of moles per unit volume will increase. To nullify this change, the reaction will proceed in that direction where number of moles decreases. For this reaction, the delta N is positive. So if we proceed in the forward direction, the number of moles increases, but we need to decrease the number of moles, so the reaction proceeds in the backward direction. For second part, delta Ng is 0, so there will be no effect of pressure on the reaction. For third part, delta Ng is positive. Number of moles increases in the forward direction. So to decrease the number of moles, the reaction will proceed in the backward direction. In fourth part, delta Ng is negative. Number of moles are decreasing in the forward direction. So the reaction will proceed in the forward direction. For fifth part, delta N is positive. Number of moles will increase in forward direction. To decrease the number of moles, reaction will proceed in the backward direction. Sixth part, number of moles, delta N is positive. Here also the reaction will proceed in the backward direction. You need to carefully observe the delta Ng. From that, if pressure is increased, the number of moles per unit volume will also increase. To decrease the number of moles, the reaction should proceed in that direction where number of moles are decreased. This can be observed by observing the value of delta Ng. You need to take care of that parameter. Next, we are completed with this question. We'll go to the next question, 27. The equilibrium constant for the following reaction is 1.6 into 10 power 5. And we gave the temperature. Find the equilibrium pressure of all gases if 1 bar of HBr is introduced in a sealed container at 1024 Kelvin. Here, they gave the initial pressure of HBr. In container, the reactant present is HBr. So we'll write 10 bar and after at equilibrium. This is at equilibrium. We'll write the pressures present, that is partial pressures of each reactant and product present at equilibrium. Here, if we consider decrease of 2p pressure compared to the initial condition, here P pressure and P pressure of H2 and Br2 were generated. So, from Kp relation, Kp is for the forward reaction, as they gave the reaction H2 plus Br2 is under equilibrium with 2HBr. They gave the Kp relation. This is for forward reaction. So we'll write in terms of forward reaction only, and we'll mention the equilibrium constants accordingly. Here HBr concentration is 10 minus 2p whole square by P into P, that is P square. From calculation, we'll get the value of P. From the obtained value of P, we can calculate the partial pressures of HBr, H2, Br2 at equilibrium conditions. We'll next go with the 28th question. Dihydrogen gas is obtained from natural gas by partial oxidation with steam as following endothermic reaction. CH4 plus H2O gives rise to CO plus 3H2. Write as expression for Kp of the above reaction. We can write the Kp expression, partial pressure of CO into partial pressure of H2 whole cube by partial pressure of CH4 into partial pressure of H2O. Here, water is not in the form of liquid, it is in the form of gas. So we could include the partial pressure of water vapor in the Kp expression. So we are done with the A part. We'll go to the B part. How will the values of Kp in composition of equilibrium mixture be affected? Always remember that Kp is only affected because of temperature. It has no effect if we change the pressure, if we change the concentration, if we change any other conditions, moles or something like that, it doesn't change. The Chatriya principle states that in order to remain the equilibrium constant fixed, the reaction either proceeds in the forward direction or in the backward direction. Finally, final conclusion is that the equilibrium constant will never change, except that if we change the temperature, the equilibrium constant will change. In B part, we'll go with the first one, increasing the pressure. From the given reaction, we have delta Ng as positive. So the reaction will go in the backward direction, but Kp has no change. The change induced by the additional conditions will be nullified by this backward reaction here. So there will be no effective change in Kp. And in second part, increasing the temperature. As the given reaction is endothermic, if we increase the temperature, the reaction proceeds forward. Equilibrium constant also increases. In third part, if we use a catalyst, rate of forward reaction and rate of backward reaction increases equally, so there would be no change in equilibrium constant, but we'll attain the equilibrium faster. We'll go on with the next question. 29. Describe the effect of addition of H2, addition of CH3OH, removal of CO and removal of CH3OH. We need to observe the reaction here. We need to observe whether the given molecules are reactants or products. If in the below reaction, H2 is the reactant, if we add H2, reactants are more. To nullify this change, the reaction proceeds in the forward direction. Therefore, the equilibrium constant remains the same. Addition of CH3OH, products are increased. So, as per Le Chatelier's principle, the reaction proceeds backward. Removal of CO, we are continuously removing the reaction. So, the reaction should proceed in the backward direction. We are removing products in the D part, removal of CH3OH. Products are continuously removed. So the reaction will proceed proceeding the forward direction to nullify this change. This question is completed. We'll go to the 30th question. At 473 Kelvin, equilibrium constant Kc for decomposition of phosphorus pentachloride PCl5 is 8.3 into 10 power minus 3. Decomposition is depicted as they gave the reaction as well as the delta H naught. Write an expression for Kc for the reaction. Here, Kc is directly we can write concentration of PCl3 into concentration of Cl2 by concentration of PCl5. Or we can write from the relation between Kp and Kc as well. Both are same. Kc into RT power delta Ng. As delta Ng in the given reaction is 1. We'll directly write the power as 1. Okay. We can either use these two of the expressions. So We'll go with the B part. What is the value of Kc for the reverse reaction at same temperature? Kc for the backward reaction is reciprocal of the equilibrium constant in the forward direction. We'll get this value. We'll go on with the C part. What would be the effect on Kc if more PCl5 is added? Kc has no effect, as I said before. Kc will have no effect if we increase pressure or concentration or number of moles or mole fraction or any other parameter apart from temperature. If only temperature is changed, equilibrium constant will change. Here, as per the mentioned change in parameter, that is more PCl5 is added, the reaction will proceed in the forward direction, but Kc has no effect. Pressure is increased. Kc has no effect, but number of units per volume increases. So the reaction should proceed in that direction where number of moles decreases. So the number of mole decreases in the backward direction. So the reaction proceeds in the backward direction for the given condition. But always remember that Kc is only dependent on temperature, not any other parameter apart from that. In third part, delta H is positive. So on increasing temperature, the reaction proceeds in the forward direction as well as Kc also increases. Next, 31st question. Dihydrogen gas used in Haber's process is produced by reacting methane from natural gas with high temperature steam. The first stage of two-stage reaction involves the formation of CO and H2. That reaction was not mentioned in the problem. We'll go on with the second reaction mentioned. In second stage, the CO formed in first stage is reacted with more steam in water. Water gas shift reaction. This is water gas shift reaction. CO plus H2 gives rise to CO2 plus H2. If a reaction vessel at 400 degrees centigrade is charged with an equimolar mixture of CO and steam, such that partial pressure of CO and as well as partial pressure of H2O both are same, that is 4 bar. What will be the partial pressure of H2 at equilibrium? We need to calculate. They gave initial values of partial pressures of CO and H2 at equilibrium. We'll consider that there is a decrease of P pressure for CO as well as H2. For the stoichiometric coefficient, the decrease is same for both of the reactants. We'll write 4 minus P and this is 4 minus P. This is P and this is P. Kp equals to P square by 4 minus P square. And they gave the Kp value as 10.1. From this reaction, we can obtain the pressure. At equilibrium, the partial pressure of H2 is P itself. We can directly write the pressure value obtained. We go on with the next question. Predict which of the following reaction will have appreciable concentration of reactants and products. Here, to determine this, we need to carefully observe the equilibrium constant values. From equilibrium constant expression, if concentration of product increases, the equilibrium constant increases. If concentration of reactant increases, equilibrium constant decreases. Here, Kc is 5 into 10 power minus 39. That is, Kc is very less. Its reactants are more and products formed are very less. So, reactants dominate in the reaction. The concentration of reactant dominates. In the second part, Kc is very large. So, products are formed in higher amount and reactants are left few. Here and in third part, Kc is 1.8. We'll get a comparable amount. The concentration of reactants are comparable with the concentration of products in this reaction. We'll go on with the next question. The value of Kc for the reaction 3O2 ozonization. This is ozonization of oxygen. Is 2 into 10 power minus 50. That is, the product is formed in very less amount. If the equilibrium concentration of O2 in air is 1.6 into 10 power minus 2, what is the concentration of O3? They gave the value of Kc, no issue. If they would have given Kp, we need to use that relation, but they directly gave the value of Kc. We can write it as concentration of O3 whole square by concentration of O2 whole cube. From this, we'll get the concentration of O3 very easily. Only this is a matter of calculation. And in 34th question, the reaction, water gas shift reaction is at equilibrium. This is not water gas shift reaction, sorry. This is formation of methane is at equilibrium at 1300 Kelvin in a 1 liter flask. It also contains 0.30 moles of CO, 0.10 moles of H2, and 0.02 mole of H2O, and an unknown amount of CH4 in the flask. They here carefully read the question that they gave the equilibrium concentrations, that is 0.3, 0.1. We don't know the equilibrium concentration of CH4, so we'll consider it as unknown X. And H2 vapor. This is vapor, so we'll include the concentration terms of H2O in the equilibrium constant expression, that is 0.02. Volume was given 1, so we can calculate the concentration by dividing it with volume. We'll write the equilibrium constant expression, that is 3.9 equals to concentration of CH4, that is X, and concentration of H2O 0.02 by concentration of CO 0.3 and concentration of H2 is 0.1. This stoichiometric coefficient of 3 will raise the power of 3. From this, we'll get the equilibrium concentration of CH4 very easily. We'll go to the 35th question. What is meant by the conjugate acid-base pair? Find the conjugate acid or base for the following species. Generally, conjugate acid-base pair differs by a proton. That is, the molecular formula of conjugate acid and base pair differs by H plus. Here, observe that HNO2, the conjugate base, this is acid, right? So we'll have a conjugate base for this acid. We have a chance of removing this H plus. So we'll form a conjugate base as Cn minus. Sorry, it's NO2 minus. And other molecule, they gave it as Cn minus. Here we can add H plus. This is base. So we'll get a conjugate acid as HCN. The other molecule is HClO4. Other molecule is HClO4. For this, if we remove a proton, this is acid. If we remove a proton, we'll get the conjugate base. And in fourth, this is F minus. This is a base as it has a negative charge density on it. It can donate electrons. This is the conjugate acid of the given base. And OH minus, if we add H plus to this molecular formula, we'll get H2O as its conjugate acid. Here, CO3 minus 2, if we add a H plus, we'll get the conjugate acid as CO3 minus. And if we further add a H plus to this acts as base as well as acid. This is amphoteric ion. So it can act as base as well as an acid because it contains H, which it can donate and act as acid, and it has a electron density which it can donate to a proton and act as base. Here if we add H plus, we can get H2CO3 as its conjugate acid. The next is S minus 2. This is a base. If we add H plus, we'll get the conjugate acid of it. If we further, this is also amphoteric. It can both act as base as well as acid. If we add another H plus, we'll get H2S. So this would be the conjugate acid of HS minus. Next, 36th question. Which of the following are Lewis acids? Lewis acids are the molecules which accept electrons. Generally, the molecules which accept electrons have vacant p orbital, d orbital, or a positive charge. Here, H plus have a positive charge. It can accept a maximum of 2 electrons. One electron. And here, BF3 has a vacant p orbital on boron atom. So it can easily accept electrons from a donating atom. Next, what will be the conjugate basis for the Bronsted acid? Here there is nothing. Here we can directly remove H plus and will obtain the conjugate base as F minus 4 HF, HSO4 minus 4 H2SO4, CO3 minus 2 for HCO3 minus. Get the conjugate acids for the following Bronsted bases. Directly add H plus. we'll get NH3 as conjugate acid for NH2 minus and NH4 plus as a conjugate acid for NH3. Because nitrogen has a maximum valency of 4, so we can make nitrogen to donate its lone pair to a H plus and further act as a base. So it can accept the proton and its conjugate acid is NH4 plus. And if we add a proton to HCO minus, we'll get the conjugate acid as HCOOH. We'll go with 39. The species H2O, HCO3 minus, HSO4 minus, and NH3 can both act as bronzodiazes as well as bases. For each case, give the corresponding conjugate acid and base. Here, the conjugate acid for this H2O is, if you need to add a H plus to obtain the conjugate acid for the given molecule. If we add H plus, we'll get H3O plus. This is the conjugate acid. If we add H plus to the HCO3 minus, we'll get the conjugate acid as H2CO3. And if we add H plus to HSO4 minus, we'll get the conjugate acid as H2SO4. And for NH3, we'll get the conjugate acid as NH4 plus. To obtain its conjugate base, we need to remove the proton. Here, OH minus for HCO3, CO3 minus 2, HCO3 minus, CO3 minus 2, HSO4 minus, SO4 minus 2, and for NH3, if we remove a proton, we'll get NH2 minus. This is the conjugate base of NH3. We are done with this question. We'll go to the 40th question. Classify the following species into Lewis acids and Lewis bases and show how these act as Lewis acid or base. OH minus, it has a pair of donating electrons, so it acts as Lewis base. F minus also acts in the similar way. H plus is a cation. It can accept electrons, so it's Lewis acid. BCl3 has a vacant p orbital, so it can act as Lewis acid. Next, 41st question. Concentration of hydrogen ion in a sample of soft drink is 3.8 into 10 power minus 3. What is the pH? pH is minus log of concentration of H plus. Here, concentration of H plus is given as 3.8 into 10 power minus 3. If we calculate its log, then it would be 3 minus log of 3.8. Then we can obtain the pH value. Here, note that pH of acids is always less than 7. pH of bases is always greater than 7. And for neutral, pH is equals to 7. 42nd question, the pH of a sample of vinegar is 3.76. Vinegar contains acetic acid, so its pH is less than 7. Calculate the concentration of hydrogen ion in it. The reverse of the formula what we use here, we need to reverse substitute. That is, they gave the value of pH. We need to calculate the value of concentration of H plus. We'll use anti-log here. Initially we need to write minus 4 plus 0.24. If we do anti-log, it will be nearly some 1.8 into 10 power minus 4. This will give you the concentration of H plus from the given pH. 43rd question, the ionization constant of HF, HCOH and HCN at 298 Kelvin are 6.8 into 10 power minus 4, 1.8 into 10 power minus 4 and 4.8 into 10 power minus 9. HF, HCOH as well as HCN were given, 3 acids were given. Ionization constant of the corresponding conjugate bases, that is for F minus, CO, HCO minus as well as CN minus, we have a relation for conjugate acid base pair, that is ionization constant of acid and the ionization constant of its conjugate base is ionic product of water. Normal room temperature, ionic product of water is 10 power minus 14. So we'll use that value. Ka is 6.8 into 10 power minus 4. For first acid, we can find Kb from the relation here. For second acid, the Ka is given as 1.8 into 10 power minus 4. We'll substitute in the place of Ka and we'll get Kb for this acid, for the conjugate base of this acid as well. And by substituting Ka value of third acid, we'll get the Kb value of conjugate base of the corresponding acid. Remember this relation. It's very useful. Go with 44th question. The ionization constant of phenols is 1 into 10 power minus 10. What is the concentration of phenolate ion in 0.05 molar solution of phenol? What will be its degree of ionization if the solution is also 0.01 molar in sodium phenolate? This is phenol. On dissociation, we'll get pH phenolate ion and a proton. At equilibrium, we can write it as alpha is degree of dissociation. Degree of dissociation is number of um, number of molecules dissociated for total number of molecules. If concentration reacted is C1, total concentration is C, that will be alpha, the ratio will be alpha. So the concentration reacted would be C alpha. C minus C alpha, and this is C alpha, as well as H plus is C alpha. From this, Ka is C alpha square, C alpha into C alpha. I'll write here C alpha into C alpha by C into 1 minus alpha. Usually these are weak acids. The dissociation constant would be very smaller than 1. So we can neglect the value of dissociation constant in the denominator. So we can directly write the denominator as C. So by simplifying this expression, we'll get this expression. Here, phenolate ion concentration is C alpha. The given concentration is 0.05. From this, we can calculate the degree of dissociation. And then first part is completed, and second part, what will be its degree of ionization if the solution is also 0.01 molar in sodium phenolate. Here, the concentration for the second part, phenolate ion concentration is given as 0.01 as the solution is present in sodium phenolate. Sodium phenolate ionizes nearly to 100%. So we'll get the concentration of phenolate ion as 0.01 molar. We can use this concentration value in the ionization constant expression. So we can directly write Ka as concentration of phenolate ion into H plus concentration. H plus concentration would be 0.05 alpha only. That would be 0.05 alpha only into concentration of phenolate ion is 0.01. Substitute the concentration directly. As the contribution from phenol is very less, we can neglect the contribution from phenol. We can directly write the contribution from sodium phenolate itself by concentration, equilibrium concentration of phenol, that is 0.05 into 1 minus alpha, but alpha is very small, we'll neglect that. 0.05 alpha is cancelled here. We can obtain the degree of dissociation value for the second condition. And we'll go on with the next question. The first ionization constant of H2S is 9.1 into 10 power minus 8. Calculate the concentration of HS minus ion in a 0.01 solution, 0.1 molar solution. How will this concentration be affected if the solution is 0.1 molar in HCl also? The concentration of H2S is given as 0.1 molar, and the first ionization constant, as it can ionize twice because it has two hydrogens. So first ionization constant is 9.1 into 10 power minus 8. This is 0.1, this is 0, and this is 0. This is the initial condition. If alpha is the degree of dissociation, then we'll have equilibrium concentrations as 0.1 minus 0.1 alpha. This is 0.1 alpha, and this is also 0.1 alpha. We'll substitute these values in Ka expression. We'll get 0.1 alpha whole square by 0.1 minus 0.1 alpha. These are weak acids, so alpha is very less than 1. By observing the Ka1, we can easily identify that formation of products is very less. So degree of dissociation will also be very less. By neglecting the alpha in the denominator, we can get 0.01 alpha whole square by 0.1. Then Ka is 0.1 alpha square. From this, Hs minus concentration is 0.1 alpha. We can get alpha square value from this Ka and we'll get the alpha value as well. By substituting the alpha value here, we'll get the equilibrium concentration of Hs minus. And in the second part, if the second dissociation constant of H2S is given, this is very, very less. Ka2 is very less. The degree of dissociation of this reaction is almost negligible. So we can directly add the two reactions, that is dissociation of Hs minus and first dissociation of H2S, and we'll get a total overall reaction as H2S gives us a 2H plus plus S minus 2. As the Ka2 is very less than Ka1, we can directly add these reactions and we'll write 0.01 minus 0.1 alpha, and this is 0.2 alpha, and this is 0.1 alpha concentration. From this reaction actually will get a decrease of concentration of Hs minus of consider some small y, and we'll have a formation of y H plus and y concentration of S minus 2. But according to the ionization constant, the y value is very small, so we'll neglect that. So we can directly add these two reactions and we can directly write the equilibrium constant expression. Here ionization constant is product of first ionization constant as well as second ionization constant, and we'll substitute the values, that is 0.1 alpha square into 0.1 alpha by 0.1 minus 0.1 alpha. Alpha is very less, so we'll neglect that. From this relation, we'll get to know the value of alpha. And from that, S minus 2 concentration is 0.1 alpha. By substituting alpha, we'll get the concentration of S minus 2. In the second condition, they gave the solution is present in 0.1 molar HCl. As the Ka of H2S is very small, we can neglect the contribution of H plus concentration from the acid. We'll just include the contribution of H plus from only HCl. We'll get a H plus concentration as 0.1 molar. This is fixed as we neglected the contribution from H2S. This is 0.1 whole square into S minus 2. This is 0.1 minus 0.1 alpha, but alpha is very small, so I neglected it directly. So from Ka expression, we'll get to know the concentration of S minus 2. Next, we'll go to 46th question. The ionization constant of acetic acid is 1.74 into 10 power minus 5. Calculate the degree of dissociation of acetic acid in 0.05 molar concentration solution. Calculate the concentration of acetate ion in the solution and its pH. Initially, the concentration of CaCOOH is 0.05 and anion is 0 and H plus is 0. At equilibrium, if alpha is the degree of dissociation, then the equilibrium concentrations are these. If we substitute these values in equilibrium the ionization constant expression, alpha is very small, so we'll neglect that in denominator. We can write the concentration of acetate ion as 0.05 alpha, as well as H plus concentration is also 0.05 alpha. By calculating the value of alpha from the ionization constant expression, from this expression we'll get alpha value. So we can get the value of concentration of acetate ion as well as H plus. From that we'll get the value of pH. Go with next question 47. It has been found that pH of a 0.01 molar solution of an organic acid is 4.15. From that we can get the concentration of H plus. Calculate the concentration of anion. Anion concentration we need to find. Concentration of anion as well as concentration of H plus is same. that is C into alpha. C is the initial concentration of the given acid. For Ka, we can directly write it as C alpha whole square by C minus C alpha, but alpha here is very small. So we'll write Ka equals to C alpha square. From all these expressions, we can find the ionization constant of acid as well as pKa is minus log of pH is minus log of concentration of H plus. Here pKa is minus log of Ka. And we'll go on with the next question, 48. Assuming complete dissociation, calculate the pH of the following solutions. Here, HCl is a strong acid, so we'll get 100% ionization. So the concentration of H plus is similar to the concentration of HCl. So we can directly write that. NaOH is also strong, so concentration of OH minus is minus log of concentration of NaOH itself. From pH plus POH is 14 at normal room temperature. Use this relation to find the pH value for a given base. Next, C part. HBr is also strong acid, so we can directly write the concentration of H plus. KOH is also strong, but here we'll get the POH value. We need to use this relation in order to find pH value. Go on with the 49th question. Calculate the pH of the solutions. 2 grams of TLOH, thallium hydroxide, dissolved in water to give 2 liters of solution. So we can find the concentration of OH minus. Initially, we'll find the concentration of TLOH. This is also strong base. So it undergoes complete ionization. So concentration of OH minus is same as the concentration of TLOH. So this is directly given as 2 grams per, its molecular weight is 221. The volume given is 2 liters. So we can find pOH from the concentration of OH minus obtained. The similar way, COH twice, if it dissociates, it gives 2 hydroxide ions. So for finding the concentration of OH minus present in the solution, you need to twice the concentration of COOH taken. We'll initially find the concentration of COOH taken, that is 0.3 grams by molecular weight of COOH twice is 74, and the volume is 500 ml. 500 ml into 1000, so the molar concentration of OH minus is twice the molar concentration of COOH twice. From the concentration of OH minus, we can obtain the POH. It's done. And then C part, NaOH is strong base, so the concentration of OH minus is same as the concentration of NaOH. So you need to find the concentration of NaOH first, that is 0.3 grams by molecular weight of NaOH by volume is 200 ml into 1000. 1000 here we are using in molar concentration, number of moles is per unit liter, not for ml. So we need to convert this ml into liter. So we'll have to multiply 1000 in the numerator. And in D part, wherever you'll find a base, you'll calculate the concentration of OH minus. You need to use the relation of pH and POH equals to 14 for finding the value of pH. Go with the 50th question. The degree of ionization of 0.1 molar bromoestic acid solution is 0.132. Calculate pH of solution and the pK of bromoestic acid. Degree of ionization is given as 0.132. It is also less than 1. It is also very less than 1. It's 1 by 10th of 1. So no problem. We can neglect it still. If not, not neglecting also, it's no problem, but the calculation would be a bit lengthier. This is at equilibrium, this is 0.1 into 1 minus alpha, this is 0.1 alpha, and this is 0.1 alpha. We'll find the equilibrium constant value, that is ionization constant here. This is 0.1 alpha whole square by 0.1 minus 0.1 alpha. If I neglect the alpha, we'll get Ka as 0.1 alpha square. From this, we'll get to know the value of alpha, and we can find the concentration of H plus easily as C alpha, that is 0.1 into alpha. and we can find the pH as well. But they ask the pH of solution as well as pKa also. Here we need to find Ka value. As they gave the value of alpha, we need to find Ka value. And from Ka value, we'll obtain the pKa as minus log Ka. We'll go with the 51st question. The pH of 0.05 molar codeine solution is 9.95. As you can observe, pH is greater than 7. The solution is basic. It is a base. Calculate its ionization constant and pKb. Ionization constant is Kb. From the relation between pH and pOH, pH plus pOH is 14. Normal room temperature. We'll find pOH value. From this, we get to know about the concentration of OH minus. From the equation, we get the concentration of OH minus as C alpha whole square by C. So Kb is C alpha square. We know the value of C alpha as well as the concentration. C term also, we also know that C term, it's 0.05. So from that, we can get alpha value from here. From this, C alpha is OH minus concentration. After getting the value of alpha, we'll substitute that in the expression of ionization constant of codeine. So we'll obtain Kb value. From this, we can calculate pKb value. 52nd question. What is the pH of 0.01 molar aniline solution? The ionization constant of aniline can be taken from table 6.7. If we revise the synopsis, we can find the value of aniline, calculate the degree of ionization of aniline in the solution, also calculate the ionization constant of conjugate acid. And aniline is a base, so we'll write ionization constant as Kb. That is similar expression, C alpha whole square by C minus C alpha. Alpha is very less, so we can neglect it in denominator. We can directly write Kb is C alpha square. C is mentioned as well as Kb is also known from that table. If we substitute these values, we'll get to know the value of alpha, degree of dissociation, God, and Ka value of conjugate acid. We have a relation that Ka into Kb equals to Kw. This is always valid for conjugate acid base pair and no other acid and base. We can directly obtain the Ka from the substitution of Kb in that relation. 53rd question. Calculate the degree of ionization of 0.05 molar acetic acid if its pKa value is 4.74. From pKa value, you can obtain the value of Ka as we can use the relation. pKa is minus log Ka. At equilibrium, we have the equilibrium concentrations as follows. In A part, they gave 0.01 molar HCl is present. Contribution from acetic acid is very small. So we can neglect the contribution of H plus concentration from acetic acid and we'll only include the concentration of H plus from HCl. That is 0.01 and concentration of acetate by 0.05 minus 0.05 alpha. Alpha is small, so we'll neglect that. Here, concentration of acetic acid is 0.05 alpha dash. From this, we can find the new degree of dissociation of acetic acid. And in B part, the concentration of H plus is varied to 0.1 molar HCl to 0.1 molar. If we substitute those values, we can get to know the degree of ionization of new degree of ionization of acetic acid. 54th fourth question. The ionization constant of dimethylamine. Calculate its degree of ionization in 0.02 molar solution. If we use that expression, that is C alpha square, alpha is very small, we can get the value of alpha here. And in second question, they gave the concentration of OH minus is 0.1. The contribution from dimethylamine is very small. So we can directly write it as 0.1 into concentration of conjugate acid by concentration of dimethylamine at equilibrium. That is 0.05 minus 0.05 alpha. Alpha is neglected here. So we can directly write the Kb expression as written here. From this, we can calculate the percentage of dimethyl ion ionized. 55th question. Calculate the hydrogen ion concentration in the following biological fluids whose pH are given below. Directly, we can write it as pH as minus log H plus. We need to calculate. And then we'll identify which solutions are acidic and basic. First one, pH is less than 7, so it is acidic. Second one, pH is less than 7, it's also acidic. Third one, pH is greater than 7, it is basic. Fourth one, pH is less than 7, so it is acidic. 56th question, the pH of milk, black coffee, tomato juice and lemon juice and egg white are given respectively. Calculate corresponding hydrogen ion concentrations. Here we can find the hydrogen ion concentrations directly by doing pH equals to minus log H plus. By finding the antilogs, you can easily find the hydrogen ion concentration. And we'll go to the next question. 57th question. They gave the weight of KOH dissolved in water to give 200 ml of solution at 298 Kelvin. Calculate the concentrations of potassium, hydrogen, and hydroxyl ions. In 0.561 grams of KOH, the concentration of KOH is 0.561 by molecular weight of KOH is 56 and volume is per liter. So we need to convert volume into liter. That is the concentration of KOH. KOH is a strong base, so it can completely ionize and it will give the same concentration of OH minus and K plus. So we can directly find POH is minus log of concentration of OH minus as well as pH plus POH is 14 at normal room temperature. Next, we'll go on with the 58th question. The solubility of SROH twice at 298 Kelvin is 19.23 grams per liter of solution. Here, from solubility of SROH twice, we can find the molar concentration of SROH twice. If we divide the given grams per liter concentration with molecular weight of SROH twice, from that we can calculate the concentration of OH minus. The concentration of OH minus is twice concentration of SROH twice. So we can calculate the individual concentrations as well as the pH of solution is obtained from doing minus log of concentration of OH minus. We'll go on with next question, 59th question. The ionization constant of a propanoic acid is, calculate the degree of ionization of acid in 0.05 molar solution, also its pH. What will be its degree of ionization if the solution is 0.01 molar in HCl also? Here, the ionization constant is given and as well as concentration is also given. So we directly write, here it is small, alpha is negligible, so we neglected in the denominator. We directly write K equals to concentration C alpha square. From that we'll get the value of alpha and from that we get the value of concentration of H plus as C alpha, that is 0.05 into alpha here. We'll find the pH from that relations. And second part, what will be the degree of ionization if the solution is 0.01 molar in HCl already? If it's present in HCl, the concentration of H plus is 0.01 molar only. The other contribution from weak acid is neglected. So we can directly write the contribution from HCl. So we can find the degree of ionization from here. Next, we'll go on with the 60th question. The pH of 0.1 molar solution of cyanide acid is 2.34. Calculate the ionization constant of the acid and its degree of ionization in the solution. The constant C is given as 0.1 molar and pH is given as 2.34. Concentration of H plus is 0.1 into alpha. As stated above, I also proved that. Calculate Ka value and its degree of ionization. From pH and C are given, so we can calculate degree of ionization as well as Ka is C alpha square. If we substitute those values, we can get Ka as well. 61st question, the ionization constant of nitrous acid is 4.5 into 10 power minus 4. Calculate the pH of a 0.0504 molar sodium nitrate solution and also its degree of hydrolysis. If the salts are formed by mixing, strong acid and strong acid are neutral. Strong acid and weak base, it undergoes hydrolysis. Strong base as well as weak acid also undergoes hydrolysis. So if we write the hydrolysis equation, we'll obtain the hydrolysis constant is equals to panic product by K. If we write C minus CH alpha is hydrolyzed, CH and CH are formed, CH whole square by C minus CH, this is KH. And from this expression, we know that KW by KA is KH. If we substitute KH value, KW by KA equals to CH square. From this relation, we'll obtain the degree of hydrolysis. We can get the concentration of H plus as C alpha, sorry, C into H, which is hydrolyzation, degree of hydrolysis. And we'll go with 62nd question. A 0.02 molar solution of pyridinium hydrochloride has pH 3.44. Calculate the ionization constant of pyridine. pH is given as 3.44. Pyridinium hydrochloride is conjugate acid of pyridine. So, concentration is 0.02 molar. pH is 3.44. From that, we'll get to know the concentration of H plus, that is CH square. And C is given as 0.02. From this, we'll get to know the degree of hydrolysis value. For finding the ionization constant of pyridine, we can directly write it as Kw by Kb. And for 63rd question, we need to identify which salts are acidic, neutral, or basic. NaCl, salt of strong acid and strong base, so the salt is neutral. For KBr, similar way, salt is neutral. NaCN, it's weak acid and strong base. So, on hydrolysis, we'll form basic solution. NH4NO3, NO3 minus is conjugate base of strong acid HNO3. So, it's a salt of weak base and strong acid. The solution is acidic in nature. NaNO2, HNO2 is weak acid. So, the obtained solution is basic. KF, HF is weak acid. So, the hydrolyzed solution is basic. 64th question. The ionization constant of fluoroacetic acid is 1.35 into 10 power minus 8. Here alpha is very small. What would be the pH of 0.1 molar acid and 0.1 molar sodium salt solution? pH here is given as concentration of H plus is C alpha as well as Ka is C alpha square. From this, we can directly write the relation of H plus concentration as well as Ka as root over C Ka. And from this, we can get the pH value. For the hydrolysis constant is Kw by Ka and concentration of H plus is CH. This is CH square. So if we substitute the value of H obtained from the above equation, we'll get H plus concentration is root over C into Kw by Ka. If we substitute the values, we can get the pH of the sodium salt of chloroacetic acid. 65th question, ionic product is given as 2.73 10 power minus 14. Generally, it would be 10 power minus 14, but here it is considered different temperature, so the value of Kw is different. pH of neutral value. So we need to find the concentration of H plus here. Neutral, as water is neutral, concentration of H plus and concentration of OH minus is the same. So if we use that, H plus concentration can be obtained. So pH is minus log of concentration of H plus. 66th question, calculate the pH of the resultant mixtures. Here you need to carefully observe whether the number of millimoles of OH minus as well as H plus are equal or not. In the first case, millimoles of OH minus are more, so the base solution would be basic in nature. You need to find number of OH minus molecules left here. So 4 millimoles of OH minus are there. 2.5 out of it will react with H plus. So 1.5 millimoles of OH minus are present in the solution. By total volume is 10 plus 25, that is 35. We'll get the concentration of OH minus. From this, we can calculate POH, and from POH, we can calculate pH as 14 minus POH. And then B part, 0.2 millimoles of OH minus from COH twice, 0.2 millimoles of H plus from H2SO4. Both are neutralized, so the above solution is neutral, so pH is 7. In C part, the millimoles of OH minus are 1 and millimoles of H plus are 2. So concentration of H plus would be 2 into 10 into 0.1 minus 10 into 0.1, as 1 millimole of OH minus is already reacted. It is neutralized into water. The leftover H plus ion concentration is 1 into 10 into 0.1. By total volume is 10 plus 10, so it's 20 ml. So we'll find the concentration of H plus. From that, we can find the pH easily. We'll go on with the next question, 68th question. The solubility product constant of Ag2CO4 and AgBr, that is solubility product KSP. The concentration of Ag plus stoichiometric coefficient is 2, so we'll raise the power of 2 here. And chromate ion concentration, here stoichiometric coefficient is 1, so we'll raise the power of 1 here. KSP, solubility is S, so we'll find the amount of Ag plus 2 present is 2S, and amount of chromate ion present in solution is S. So KSP, we'll substitute these values, 2S whole square and S. We'll get an expression of 4S cube. And on substituting the KSP values and doing calculation, we can find the solubility of Ag2CrO4. And in similar way, AgBr, if S is the solubility of AgBr salt, we'll find the amount of Ag plus as S and Br minus as S. After achieving its equilibrium, KSP is S squared. By substituting the value of KSP, we'll find the solubility. 69th question. Equal volumes of 0.002 molar solution of sodium iodide and cupric chlorate. Equal volumes were present. As both of them were mixed, the volume becomes twice, so the concentrations will become half. Here, we need to carefully identify whether on mixing these two solutions, the precipitate of cupric iodide is formed or not. To find that, we need to find the ionic product and its comparison with solubility product. We can find the ionic product for the following: solubility of CiO3 minus 2 is concentration of Cu plus 2 the concentration of IO3 minus 2 whole square. This is ionic product is Cu plus 2 whole square. Sorry, Cu plus 2 into IO3 minus whole square. So, by calculation, we'll get ionic product is less than solubility product. So, there is no formation of precipitate. Still, the equilibrium concentration of product is not reached. So, it will not precipitate. So, there is no possibility of precipitation here. For finding such cases, you always need to take care of the ionic product value. If ionic product value is smaller than KSP, then the precipitation is not formed. If ionic product is smaller than is greater than the KSP, then the formation of precipitation is possible. Next is 70th question. The ionization constant of benzoic acid is 6.46 into 10 power minus 5 and KSP for silver benzoate is 2.5 into 10 power minus 18. How many times is silver benzoate more soluble in a buffer of pH 3.19 compared to its solubility in pure water? Buffer is a solution where pH remains constant for small changes done in the solutions. Like if we change the amount of water, that is, if we dilute, only limited changes will be tolerated by the buffer. If we have a large changes of concentration of H plus or OH minus, surely the pH of buffer will be affected. Only for small values, the pH can remain same for a buffer. Here, we'll write the relation for Ka because sodium, sorry, here silver benzoate, we'll consider the salt silver benzoate hydrolysis also. Because buffer, it has a concentration of H plus. From the Ka relation, we can easily find that ratio of concentration of CH3 benzoate and benzoic acid. We'll find the ratio initially. And then if S is the solubility, how much the amount of silver benzoate is converted into benzoic acid, that much amount will be soluble. So the concentration of benzoic acid is same as the concentration of benzoate. The hydrolysis is compensated with the solubility. So the concentrations are same, and let us consider it as some S. And here, total concentration, that is C6H5COOH concentration plus C6H5CO minus. Let us consider this as some Y, and solubility is given as its hydrolysis, that is the amount of C6H5COH and the amount of benzoate ion present. So on addition, we'll get this expression. In KSP, substitute the values of Ag plus. We consider the Ag plus ion concentration is solubility, that is S, and C6H5CO minus because of the presence of H plus. Here the key point is that it undergoes hydrolysis. We need to consider the concentration of C6H5COOH also. It will also be formed. The amount it is formed, that much amount it will be soluble. By using that logic, we can easily find the relation, and finally we can obtain the solubility in presence of a buffer of pH 3.19. And now the solubility in pure water is very easy. Let us consider the solubility as X directly. Same, just because on ionization, that is on dissolving, the silver benzoate gives stoichiometric coefficient for both silver ion as well as benzoate ion as 1. So we can directly write X into X is X square. So X is root KSP. Here they ask the ratio of solubility of silver benzoate in pH of 3.19 and solubility of silver benzoate in water. By finding this ratio, we can directly find the value as in the question. Next, we'll proceed to the 71st question. What is the maximum concentration of equimolar solutions of ferrous sulfate and sodium sulfide? Here the formulas, molecular formulas are FeSO4 and Na2S. When we mix these two, FeS is formed or not. We need to find that. As I said, to find that what is the maximum concentration of equimolar solutions, if we consider C concentration of ferrous sulfate is present and the C concentration of sodium sulfide is also present. So these are mixed in equal volume. So volume and volume on mixing, it will become twice. So the concentration will become half. This is C by 2 and C by 2. As FeS is formed, we can write KSP as C by 2 into C by 2 whole square. Maximum amount to prevent precipitation. So we'll equate it for the maximum case initial, but inequality will remain the same. That is, ionic product should be less than KSP. In that case only, when we mix these two solutions also, we'll not find any precipitation. So for finding the maximum value, we'll equate it to the KSP. We'll find the limiting value to prevent it from precipitation. By equating it to KSP, we'll find the concentration, equimolar concentration of these two solutions such that there is no precipitation of iron sulfide. We can find it directly here. We'll proceed to the next question, that is 72nd question. It is, what is the minimum volume of water required to dissolve 1 gram of calcium sulfate at 298 Kelvin? For calcium sulfate, the KSP is 9.1 into 10 power minus 6. Here, we can directly find the solubility as S square equals to KSP. From this, solubility is weight per unit volume. So, weight of CaSO4 is given as 1 gram and per unit volume. From this relation, root KSP equals to 1 gram per volume. We can easily find the volume of the solution. Now, heading to the last question of this exercise. The question is, the concentration of sulfide ion in 0.1 molar HCl solution saturated with hydrogen sulfide is 10 power minus 19 molar. If 10 molar of this added to 5 ml of 0.04 molar solution of the following FeSO4, MnCl2, ZnCl2 and CdCl2. Here, if we need to observe whether the mixing of these two solutions gives a precipitate or not, we need to compare the ionic product with the solubility product. To do that, initially the concentration of S minus 2 is given as 10 power minus 19 and total volume is given as 15 ml. Here, this concentration of S minus 2 is for 10 ml. So we need to find the concentration of S minus 2 for 15 ml. So therefore, the concentration of S minus 2 is 10 power minus 19 into 10 by 15. And if we consider the metal ion concentration, it is 0.04. That concentration is for 5 ml. If we find it for 15 ml, we'll get the respective concentrations of S minus 2 and M plus 2. If we find the ionic product, that is M plus 2 into S minus 2, we'll get some value. If that value exceeds the KSP of the given salt, then precipitation takes place. If not, precipitation will not take place. We can check these values from the tables present in the NCERT chapter. So always remember that. Never forget in order to compare, in order to find that whether the solution is precipitating or not, the ionic product must compulsory exceed the solubility product. Hydrolysis, you need to consider if a salt is produced from either weak acid or weak base. You need to consider the hydrolysis of salt. Hydrolysis of salt, because they are weak, the degree of hydrolysis can be neglected in the expressions. So you can directly write KH is as CH square, as well as KH equals to KW by KB. Depending on the nature of the salt, you can write it as KW by KB or KW by Ka. From that, we can find the concentrations of H plus easily, as well as the hydrolysis constant value, and as well as degree of hydrolysis as well. To compare whether the solution precipitates or not, we'll just compare the ionic product and the solubility product. If ionic product exceeds, then precipitation takes place. And equilibrium, important note to be taken. Here, active masses of pure solid and pure liquid will not be included in the equilibrium constant expressions. And you need to take care of the stoichiometric coefficients because they will be raised as power to the concentrations of partial pressures in the equilibrium constant expression. As well as alpha is negligible for most of the weak acids. But here you need to identify the ionization constant very well. If it is in the range of 10 power minus 2 or something, the neglecting of alpha won't work. It will give some error value. So that is not appreciated. So you need to take care. If it is in the range of 10, order of 10 power minus 5, 10 power minus 6, then you can neglect alpha and you to reduce your calculation and you can easily perform the calculation accordingly. But you need to identify the ionization constant values and do further calculations. If neglecting is possible, then you neglect. If neglecting is not possible, then you don't neglect. If you neglect, you'll get a different value and you'll not get the correct answer. That is not good. And as well as you need to take care of the concentration of OH minus, right? We are using the concentration of OH minus. OH minus concentration is used when a solution is acidic, when a solution is basic. And if it's acidic, then we'll use the concentration of H plus because H plus in concentration and OH minus concentration will be significantly present in their respective natured acids or bases. So we can easily find. And that's all. And other, apart from that, equilibrium requires more calculation and some approximations according to the equilibrium constant values. And that's it. Thank you for this session.